this stuff's been worked on and looked at for decades. I mean, for instance, at the Gulf Coast Carbon Center at the BEG. And then, COVID happens and the green shift kind of is gaining steam. And, let's see, last year, you see big companies like Exxon starting to show interest in carbon capture in the Houston area. And of course, again, the researchers have been on this for a while, but you see some stakeholders here putting together potential or conceptualizing this, developing CCUS hubs in the Texas area. But looking over in the European side, and we're focusing mainly in North Sea here, things have been ramping up rapidly over in the North Sea. I mean, we have several projects being developed over the next 5 to 10 years. Mainly, one of the biggest ones is this Porthos project in the Netherlands. Green sand is kicking off here in Denmark in a few years, and also you have some of the bigger names like Acorn, Endurance. Some of these names you might have heard of, Zero Carbon Humber. And then you have Sleipner over here in the Norwegian sector, which is probably one of the most famous CO2 storage success stories. And then you have this area here. It's referred to as Northern Lights on this map, but this is my little postage stamp that I've kind of grown to know and love, and will be the focus of this talk. So since I joined UIO, I've been working under the Norwegian CCS Research Center. It's an industry-driven, science-based innovation center to fast-track CCS deployment. It started off in 2016, and it looks to run until 2024. Here's the budget. Pretty big money going into this research center. Half of that's coming from the Research Council of Norway, and then from stakeholder partners. And then there's 12 research tasks. So the whole center is divided into 12 tasks, and I'm part of this task 9, which is over here, the structural de-risking or geological de-risking. And that's led by Ellen Skurtveit at the Norwegian Geotechnical Institute. And then my supervisor is Alvar Boen, who represents the University of Oslo. And you can see some of our stakeholders here involved with the project. But all that out of the way, here's a bit about the project motivation for my PhD. So most of us are aware now that CO2 storage volumes must be upscaled dramatically to meet climate mitigation goals set by some of our governments, and a lot of people are starting to realize this. So in the North Sea, injection at the Aurora site, so that's going to be located just offshore. This is Norway here, just offshore in the northern North Sea. So it's a location called Aurora. The whole project's called Longship, and that involves capturing the CO2 from industrial point sources in Oslo and other parts of the eastern Norwegian coast, and then that'll be shipped in vessels over to a processing plant in western Norway, and then piped into to the storage location. And that storage location is known as the Horda Platform, it's Aurora is in the Horda Platform. And with this project kicking off, the Horda Platform and the Norwegian Continental Shelf might become one of Europe's big CCS hubs. We can utilize the geology there. We can utilize the developing infrastructure and the know-how to develop it into a hub. In that location, there are 2 strong storage complex candidates. So when I say storage complex, I'm mainly talking about just the reservoir and seal pair. Some people say caprock, I usually say seal. And those 2 are the lower and the upper Jurassic intervals, and those are going to be saline aquifer, sandstone aquifers. And I wanted to give a brief description of the location here. So this is the schematic of the Aurora site, and here's the well that was drilled 2 years ago, which will be potentially the injection well for the first phase of the project. And so injection will be about 1.5 megatons per year at this site, and then maybe as things progress, they will ramp it up to 5 or more as things go. Well, with regard to my PhD project, which is mainly focusing on geological risks to CO2 containment, I'm mainly focused on the distribution and the natures of the top seals and lateral seals. So when I say lateral seals, I'm talking about fault seals in relations to the traps. And then we want to know, seal thickness. We want to know what the overburden geology looks like and the arrangement of those units along faults. And then we want to know the unfavorable juxtapositions and evaluate those membrane seal potentials where needed. The problem is the properties of sealing lithologies, especially in fault rocks, are important, but are difficult to predict. So we kind of start from a basic, juxtaposition or other kind of simple models, and then can kind of go from there. But we also need to know aspects of the regional plumbing system and other and the past and present kind of plumbing system of the basins that we're working in. So in my project, I've been using mainly 3D seismic, but a little 2D, and then well data and reports. So here's just a really quick summary of the ongoing studies in the area. So this is the main study area here. You see Western Norway here. Here's that processing center I was talking about, and here's the pipeline being built over to the Aurora site. Here's the possible injection well. And the orange is the outline of the 3D seismic that I've been using, and this hard outline is the main study area that I've been focusing on. And I've worked on 3 topics. You can see I've color coded them based on the interval of interest that they pertain to. And the first one is a comprehensive trap and seal and mapping analysis of the area. And then I've also been working on a detailed characterization of seal deposition and lithology, and also been mapping the overburden for any fluid escape structures. But in this talk, I'm mainly just going to focus on the first one. And that's just to save time, really. So finally, we'll just jump into the geology. And for those of you who aren't very familiar with this northern North Sea area, so the study area is located here in the Horda Platform in the northern part of it. And the North Sea Rift Basin began to rift in the Permian to Triassic, and then later again it experienced another phase in the late Jurassic and early Cretaceous. This region is well known for hydrocarbon exploration and production, mainly from the Jurassic interval. But again, we're talking about CCS here. So as I mentioned before, there were 2 primary storage complexes that we're looking at. The first is this Lower Jurassic one. Don't get too hung up on the formation names, mainly just gonna refer to them as the lower and upper storage complexes, and the storage aquifer versus the seal, that type of thing. But you see the formation names here. The Johansen and Cook formation sandstones are the aquifer, and the top seal is the Drake formation. Here's the stratigraphic column here in a log showing that. So here's the Lower Jurassic. You can see those Cook and Johansen sandstones overlaid by the Drake mudstones on top. And then you have a gap with the Brent group, and then on top of that is the Upper Jurassic storage complex, which is the primary petroleum system, or the producing petroleum system in the study area. But the aquifer that is kind of the potential aquifer for CO2 storage is the Sonjefjord and Fensfjord sandstones, which are capped by the Johnathon formation, and these Cretaceous units here as the potential seals. And then but for the most of this talk, I'm going to focus on 4 large fault blocks, just to kind of partition the results, and also to kind of keep things organized. And I'll show you those in these cross sections here. So here's just an east to west cross section in the Horda Platform, interpreted from 3D seismic. I'll show you some seismic later, but this is just a schematic just to get your eyes adjusted to the geology. So again, those 4 major fault blocks here are the Troll fault block, and that's bound by the Svartalv fault block and the Troll fault zone. So the Troll fault zone, the Svartalv fault zone, and then you have the Svartalv fault block, and then that's bound by the Tusa fault zone, and then the Tusa fault block, the Vedifault Zone, and then, oh, there's a curveball. There's this Snehaya fault block, but then that's bound by the Øygarden fault zone. That's the main basin bounding fault right there. You can see in the purple, the large Triassic wedges from the primary or the first rift phase in the basin, and then some post-rift units in the late Triassic and the Cretaceous, the Jurassic. And then later in the Jurassic and into the Cretaceous, you get that second rift phase. So you get these large wedges in the hanging walls, followed by post-rift sediments in the Cenozoic. Here's the troll field for kind of reference. And here's the Aurora well, again, kind of coming down into that lower Jurassic interval, just to give you a sense of where things are. But if we strip all that away, we're going to focus again on those CO2 storage complexes in the Jurassic. So here's, I've color coded them based on, if there's the storage aquifer, they're in yellow. Intermediate aquifers are, kind of unimportant aquifers are in orange. And then the seals are in gray. So the primary seal or the immediate top seal is that darkest gray. And then you have lighter grays as you go up, the secondary and tertiary seals. So injection would occur sometime in Aurora, or in 2024, and migrate into the plane of this cross section, actually not kind of to the east as you might see here, towards the Troll West field, but under the Troll West field. And then in this fault block, you have obviously production in the Troll East field, but then in the Snehaya fault block, you have no discoveries, which is quite interesting, but it lends itself an opportunity for more CO2 storage, actually. So before I go into trap and seal analysis, I wanted to first map out kind of the aquifer, the gross aquifer presence. Is there somewhere, or is there reservoir to even inject to in this fault block? So I use the seismic data to map the top and the base of the Jurassic storage aquifers and then derive their thicknesses. You'll see that in this presentation, I'm using color bars that are maybe a little bit unusual to what you're used to, maybe these rainbow ones that you're used to from Doctoral or whatever you're using. I'm using these scientific ones. They're more chromatically uniform and they're easier on the eyes for colorblind folks. So I really encourage you to look into this. This is a UIO researcher who's developed these particular color bars. You can download them for free and use them and import them into most software packages that you're using. But anyway, back to the geology. So again, the map on the left is going to be your lower Jurassic gross aquifer thickness. So as you can see, the darks are thick and the lights are thin. So the east, it's quite thin. It's below 50 meters, but as you go towards that Aurora area right over here, it's as thick as 200 meters. So quite a lot of sandstone going over to the west, and then obviously to the northwest. In the Upper Jurassic, it's a little bit of a different story, quite a lot thicker, actually. That gross aquifer thickness ranges between 200 to 500 meters. Throughout the Horda Platform, sort of thicker in the middle of the study area, and obviously off the Horda Platform, it gets a lot thicker. But in general, yeah, pretty thick and rather present. So if you look at the well data, it also suggests lateral continuity. So if you look at this lower Jurassic sandstones, the gamma ray shows a good reservoir character, and then also same with those upper Jurassic sandstones. So now that we know that we can map pretty much all the structures and confidently and know that there's reservoir present, I wanted to start to look at the fault. So here's just a generalized fault characterization. These are maps of variance attributes extracted from both the top of the Lower Jurassic storage aquifer and the Upper Jurassic storage aquifer. The main fault sets you'll see is these north-south trending large faults in both of the maps. You can see that the maps don't differ that much because they experienced a lot of the same kind of events. But yes, these north-south trending faults are the largest. They originated in the Permian through Triassic rift phase, and then were reactivated later on in the Jurassic and Cretaceous. And then they have throws over a kilometer usually, and they're mostly thick-skinned or displace the basement rock. Then you'll see these northwest, southeast, and these northeast, southwest trending faults here and here and so on. Those originate mainly in the Jurassic through Cretaceous rift phase, and they usually only are displaced they displace the sediments less than 100 meters typically, and are confined to the sedimentary section, so they're not really thick-skinned compared to the other ones. But they create the traps for hydrocarbons and potential CO2 storage locations in this area. And above the Cretaceous, you have lots of polygonal faults in the Cenozoic, but I'm not going to really get into that in this talk. So now we know where the faults are. Let's map the traps. So here are two structure maps. This is the top of the Lower Jurassic, and here's the top of the Upper Jurassic aquifer. There are many structural traps, so you have 95 mapped in the Lower Jurassic and 64 in the Upper Jurassic. They're nearly all footwall traps. That's not really surprising, actually, but there are a couple of hanging wall traps, mainly over here on the western side or kind of along the Øygarden fault zone. And most of the larger traps are abundant. The largest traps are typically found on the north-south trending faults because they're the largest. That doesn't shock us. But here's some statistics on that. You don't see a lot of, the correlations are extremely great as you have closure area versus closure height. And here's just a distribution of the gross rock volumes for all those traps here. Yeah, in general, you see that I've combined actually the troll field accumulation as one, because it is actually a fill to spill closure through all these fault blocks here. So that's this big peak in the gross rock volume here, but it could be used for EOR someday, or maybe like after the production halts in 2050, they might use it for CO2 storage, who knows. But now that we know where the traps are, we can think about, okay, well, is there seal on top of those traps or on the side of those traps even? For the Lower Jurassic, you have thinning to the northeast. Thickness, it's hard to map with the seismic resolution. It seems like it goes to 0 towards the very edge of the study area. But again, in this Aurora area here, you have thickness over 150 meters. So lots of seal on top of where they're going to be injecting CO2, and definitely above a lot of these other traps mapped here. In the Upper Jurassic, it's a little bit different. You have thickening in the hanging walls of some of these large north-south trending fault zones, obviously from the second rift phase. And then you have a thinning, especially over Troll West, but it looks like it says 0, but in reality, I didn't map the third seal here. So there's actually another seal on top of these areas that are 0. That's what's keeping all this oil and gas in place. So even though it says 0, there's actually quite a bit of seal still left on top. But we know now that mapping these seal intervals, we know that there's proven seals, at least in the Upper Jurassic, and there's definitely seals present in the Lower Jurassic too. But what about the lateral seal continuity? So this is where we start to look at the faults. And I first look at a cross-fault juxtaposition as the primary analysis here. So yeah, where the faults are, where the throw is less than the seal thickness, then we have juxtaposition seals. And those are mainly the small interblock faults. And then when the throw is greater than the seal thickness, then you need membrane seal, because then there's typically a reservoir or some other kind of like high permeability unit past that seal. That's something like the Tusa fault zone. And the thick-skinned faults are the ones that really have these large closures, but they also have these large areas where the throw is greater than the seal thickness. So we have to have a membrane seal. So here's just the interpretation played over that seismic. I'll flash back and forth a couple times here. You can see the distribution of, at least in the Upper Jurassic, you can see the potential areas for juxtaposition seal. Obviously, Troll is sealed by this by these seal units here, but then you have CO2 storage potential in these small closures here, and over here in the Smehaya fault block. There's a couple I've mapped, and then in the Lower Jurassic are the most interesting, but in that they are the displacements along these large faults like the Svartdal fault block. You have a closure here, and then juxtaposition against an aquifer. So you need a membrane seal here to store it. And so we can run through a couple other cross sections here. Here's another one just further to the south. You can see the location of the line here on the lower right. So here's just another cross section running through the area, and I'll just jump back and forth again just so you can train your eye. Oh, went the other way. All right. So this cross section goes through the Aurora well. So you have migration will probably occur, up dip towards this Troll West area, but underneath it. And you get some small closures along the way that'll probably soak up some of the CO2 and trap it as it migrates up into this larger, greater closure up here. In the Tusa fault block, again, you have these really large closures or large traps which need membrane seal, and you kind of get the picture as you move north to south along these cross section here. Here's another one. And you can also see that the structural complexity really diminishes as you go further to the south. So here's just me flipping back and forth with this interpretation again. And this is the southernmost line here. But so you get the tail end, or the southernmost part of the Troll East closure. That's obviously juxtaposition seal here. To the east of that field, you have lots of potential storage potential in the Upper Jurassic, and then again, these Lower Jurassic ones generally require membrane seal or at least the largest ones require membrane seal, as opposed to these kind of smaller ones where you could probably rely on juxtaposition seal. So the next thing I'm going to do is show Allen diagrams of at least one fault zone here. So this is the Vedifault Zone. So we're going to show an Allen diagram here. Hopefully you guys are pretty familiar with those by now. So right now we're looking to the east towards the Vedifault Zone. And there's two segments here. There's one to the north and one to the south. In general, so for the Lower Jurassic, you have really, there's one closure that I've mapped here, which looks like it could be sealed by juxtaposition seal by actually the Cretaceous units. And then, but to the south, there are no traps here, but you can see that there's no juxtaposition seal. It's all sand on sand of the Upper Jurassic juxtaposed against the Lower Jurassic. So the Lower Jurassic is in the footwall, and then the Upper Jurassic and the hanging wall is juxtaposed against it. And then if we look in the Upper Jurassic, we really don't have, there's no membrane seal to really worry about here. We mostly have juxtapositions of the Cretaceous units against the Upper Jurassic aquifers. This alpha prospect is a pretty well-known, well-studied CO2 storage prospect in this area, in this Smehaya fault block. So that's why I've labeled it alpha. But yeah, so those rely mainly on juxtaposition of these primary and secondary seals here. But what's really interesting is this sandstone on sandstone juxtapositions, these membrane seals. Like, how do we understand if they can seal or not? And one way to do that is with pressure data. So here are pressure profiles from 3 wells in the 3 different fault blocks. We have drawdown or pressure drawdown from production and Troll in the Upper Jurassic. So you can see here's just an example, or these are examples from west to east. So the Svartdal fault block, the Tusa fault block, and the Smehaya fault block. You have production in these 2 fault blocks, and you have obvious drawdown and pressure from hydrostatic here. And then even in the Smehaia fault block, which has no production, it has drawdown, pressure drawdown across this fault and across the relay ramps. These wells are drilled after production, so we can trust the data there as far as the pressure conditions. But there's no observable vertical communication between the Upper Jurassic and the Lower Jurassic. You can see the Lower Jurassic aquifers are in line with that hydrostatic trend here. So you have depletion in the upper part and no depletion in the lower part. So we have some idea that the top seals are working. Well, what's the most interesting to me is that you have depletion in in the Upper Jurassic, but you don't have depletion in the Lower Jurassic across this Vedifault Zone, which has sandstone on sandstone juxtapositions. So this leads me to believe that there's some sort of permeability barrier here confining the pressure from drawdown here and keeping this at hydrostatic. So maybe that has something to do with its fault seal capability, because we don't have any communication here across this, and we don't have any data. We have some data down here, but we don't have any data here in the Tusa fault block to say the same thing across this Tusa fault zone. But if we use SGR maybe to try to use it as a proxy for any kind of fault gouge or entrained low permeability rock within the fault zone. Here's just our shale gouge ratio model. I'm going to take away the areas where there's juxtaposition seal and only show the areas that have sandstone on sandstone juxtapositions. So what's interesting is that the areas where you have the Lower Jurassic juxtaposed against the Upper Jurassic, we have high SGRs that are higher than 0.15 or 0.2, which is typically a good number in the SGR world if you're a fan of that, or if you've seen a lot of the correlation work in the North Sea and other parts. So high SGRs in these high displacement areas where you have the sandstone on sandstone juxtapositions of the two storage complexes. You also have poor SGRs where you have self-juxtaposition. So where, like, say, the Upper Jurassic is self-juxtaposed, you have poor juxtapositions. And that's actually interesting because then that explains that pressure communication across relay ramps and so on from that previous figure. So if there's high SGRs and no pressure communication across these sandstone juxtapositions here, then that might also tell us that there's some sort of fault seal, and that's an upside for anybody wanting to store CO2 in that Lower Jurassic interval. And I don't have time to show you these other. I've done a few other figures here about this, but yeah, the results are generally the same for the other faults that I've mapped or that I've modeled in the study area. So let's just move on to the summary here. It looks like we're pretty good on time. If anyone has questions or if I skipped over anything, we could definitely, I'm definitely all ears, or I'm here to answer any questions, but we'll just run through the summary here. So of course, more CO2 storage is needed, more. That's I hope that's something that everyone can agree on right now. And I think it's good for us geologists to, have more work to do. So the Lower and Upper Jurassic storage complex have high potential, I think, in the Horda platform. There are many viable structural traps in the study area, and the top seals are mapped. I mapped them and seem present, and the pressure data also confirms that. So in the Upper Jurassic, the main conclusion is that cross fault juxtaposition seals seem to be the primary sealing mechanism for not only the troll field, but also just for any potential CO2 storage in the area. So that's something that, of course, you might want to start looking at lateral facies changes and things like that, or even vertical ones to kind of de-risk those potential traps there. But for the Lower Jurassic, it's a different story. The fault membrane seal is required for many of the traps that are the most attractive. But what's nice is that the shale gouge ratios and the pressure data agree in that they suggest that the membrane seal is present. They're high shale gouge ratios and across fault pressure differences between the lower and the upper Jurassic juxtapositions. So we'll kind of return to that question. Can the Horda platform, so that's over here, can that become a future CO2 storage hub for Northern Europe? And you know, I think the results here are positive. A lot of work still needs to be done. You know, monitoring is a big issue. You know, development. Where do you go next? Are structural traps actually necessary? Can we just use just large up-dip migration and residual trapping instead of structural trapping? A lot of the governments like structural trapping just because, you know, everything goes into one place and it's easy to monitor. But anyway, I think there's a bright future, at least in Norway. There's a lot of competition about to happen in the North Sea, though, so it's going to be really cool to see how it all plays out over the next 50 years, I guess, or I guess it's supposed to be 25 years. But anyway, all this work's actually now in a manuscript in press with AAPG Bulletin, but it's the preprint, which I submitted last June, is available on Earth Archive here. So if anyone's interested, you can pull it out. But my email's on the, you know, or I can also share my email. So just shoot me an email. I could send you the latest version of the manuscript. So with that, here's just a thank you to the data provider CGG, ACT Labs, for some of the work that they've helped with some samples that I had, and software providers, and then also the NCCS acknowledgements. Here's my email if you have questions or if you want a preprint or whatever. And then again, here's that link to those color bar maps that I was using from the University of Oslo. Here's the guy, Fabio, that made them. So yeah, shoot them an email. They're really helpful. But with that, I'll sit back and take any questions. Thanks, guys.
Thanks, Jonathan. We've had one question come in so far, so I'll read that to you while others are coming in. Great talk. The question is, how would CO2 typically be captured, and how would you make sure the captured volume is not exceeding the reservoir volume prior to injection?
Well, the volumes are huge. So about 10 years ago, the Norwegian Petroleum Directorate, they, which is kind of like the BOEM, or kind of like that, well, it's a state agency that runs the petroleum and activities in Norway. They made a CO2 storage atlas, and the potential volumes that we're talking about in the North Sea, or at least in the Norwegian Continental Shelf, are in the gigatons, so tens of gigatons. And that's a big number, but it's still not the number that we need to store globally, but it is useful for Europe. And so I mentioned before, the project Longship will start its capacity at 1.5 megatons per year. So that's million versus billion tons. I mean, I think Aurora has a capacity, I can't remember the exact number, but it's out there, and it's definitely much lower than 1.5 megatons per year, and they're going to ramp it up to 5. But as far as capture goes, that's more of an engineering question. The capturing is going to be, again, focused on industrial sites. So in Norway, this first phase of the Northern Lights project will be capturing CO2 from a CO2 plant, and so and other smaller sources. So CO2 plants, they, you know, and other industrial sources, they produce a lot of CO2, and they're unavoidable emissions. So the CO2 storage is necessary for those types of industries, and so that's where the CO2 will be captured from. And like, again, that's kind of not my, I'm a geologist, I'm not so familiar with that, the capture side and the transport side, which is also quite fascinating. But that'll be, again, once it's captured, it'll be liquefied, and then, or supercritical, turned into a supercritical form, and then put on a boat. And that it'll be further processed somewhere else in Western Norway and then injected. So sorry, I'm not the best for the capture side, but the volumes are definitely there in the North Sea.
Okay, thanks. Next question, really nice presentation. Have you guys considered the possible interaction between CO2 and the hydrocarbon residue within the fields?
Right. Yeah, and I think the short answer to that is no, because they want to avoid it. There are, at least in the Northern Lights project, there's no plans to inject CO2 into a producing field or an abandoned field. So the goal is to inject into fresh, or not fresh aquifers, but to saline aquifers that are they're not charged with hydrocarbons. And that's to, I think there's two things to it. You have greater capacity. Unfortunately, you have less data there, but you have greater capacity likely if the geology is good. And then also, it's a bit of an unpopular move at this moment. I think, especially in Europe, is to use it for EOR. I mean, there are universities doing research on those types of topics, but in Norway, I think it's a bit of an unpopular move to use the CO2 storage as EOR. But I think eventually, like I was saying before, once Troll goes out of production, sometime in 2050 or 2060, it'll be an attractive place to put CO2. It's a huge trap, and it's known to be a good seal, or at least it's sealed 250 meters of gas. So that's definitely an attractive place. So I would say, I think it's just a matter of research, but no, I have not done that.
Okay, next question. Your definition of the Upper Jurassic complex seems to include some Lower Cretaceous section. Is that significant for some reason?
Let's see, the Upper Jurassic complex. Yeah, so the complex, then I named it after the reservoir. So I named it after the storage aquifer. So the Upper Jurassic, yes, the seals are Upper Jurassic, and they are Lower Cretaceous and even Upper Cretaceous and even Paleocene. So Troll Field, for instance, has onlapping or even eroded seals to the point where that actually it requires the Paleocene to seal it. So yes, I guess it's a matter of nomenclature. How do you name the storage complex if you're going to use a geological term? I kind of use sort of the play analogy, like if you say the Eagleford play, that's that's a Cretaceous play, I guess. But I kind of named the storage complex after the storage aquifer.
Okay.
Hopefully that answered the question. I don't know.
Next question. Does your group anticipate longer-term fault sealing by carbonate mineralization in and around fault zones, or is that too risky?
No, I think that's a good, I mean, the problem is that we're in such early days in this research. I mean, my group hasn't really focused on it. I think this is kind of a small scale problem, but there are people in UIO that are working on it, and other universities are working on this mineralization issue, or not really an issue. It's a part of the storage process. It's a mechanism that they can use too. But it can also help the seals. It can also make things a little bit more difficult for injectivity. This is a little bit beyond my means. I'm not such a great mineralogist or a chemist, but the CO2 can dissolve the carbonate material in the fault zone or in fractures. It's the carbonic acid that's produced from the interaction of the water and the CO2 that's injected. But after that equilibrates, it actually then you have the mineralization occurs. So these are timescales that also are kind of a little bit beyond the immediate injection too. So to be honest, this is kind of a modeling that, you know, this is an avenue of modeling that I'm not even prepared to do, but I think there are many people who are. So I'm really looking forward to the research that's going to go into it. I think the operators do a little bit of that, but you know, again, it's early days, so I think we're still kind of learning about how to do it.
Okay, good stuff. Next question. Do you think the fault membranes on Jurassic sand on sand juxtapositions are efficient throughout the Horda platform, or is it only a local feature?
Right. I mean, it kind of depends on your philosophy. Yeah, I mean, it's a bit of an issue. What's annoying is that you can't really know until you inject, and it's kind of the same way with hydrocarbon exploration. You don't know until you drill, type of thing. I mean, you can do a lot of preliminary work. You can do modeling. You can do trying to understand the geological history, the burial history, and so on, and do SGR analysis or whatever kind of fault seal analysis you choose. Use field analogs, things like that. In the Horda platform, I think it depends on kind of, you know, it depends on orientation, it depends on displacement, it depends on a little bit of the lithologies, but my models show basically the same kind of phenomenon with at least the same kind of results with the shale gouge ratio, that they are high when the displacement is, it puts these two saline aquifers against each other, because the displacements are large and you have quite a bit of fine grain material within the sedimentary section to kind of put lower permeability rocks, or, you know, mechanically or whatnot, into the fault zone to make it this way. But you know, in the paper, I go a lot into this. I feel like it's a bit of a question. It's one of those questions that you could answer for a long time, but I would say short answer is yes, but I think there's a lot of things to consider. It's like, I think not all faults all faults is a dangerous word, but in the North Sea, you know, there has been work shown, you know, some analogous areas have shown that, you know, the fault seal is pretty consistent in some, depending on, you know, fault orientation or displacement and so on. So yeah, sorry, it's not also a really concrete answer there, but I do go into it a bit into the paper. So yeah, look at there.
Yeah, definitely need to check out the paper. The next question, have you done any work on leakage potential from fault reactivations during production or from the planned injection?
Right. No, I haven't. There are people at the Norwegian Geotechnical Institute. There's, I mean, the fault reactivation and geomechanics of the injection is still being kind of analyzed. You know, what's 2022. The injection's supposed to start in 2024. Again, the operators probably have done a lot of work on this, but maybe not to the degree that academics would. And so right now there are a few in my university that have put out some papers. I've been involved with one. But right now the stress field doesn't really lend itself to reactivation though. It's oriented in such a way that the reactivation potential is not so great with, or not so it's more advantageous than other orientations and the magnitudes too. So this is just another aspect that needs to be done and is being carried out, but by other people. So there are some other papers. I can always point to a few, but there are more and more coming out.
Okay, next one. You use SGR to characterize seal. However, the observed depletion is through the aquifer, so the faults do not offer membrane seal. The absence of depletion indicates a sealing fault acts as a permeability barrier to fluid movement. Have you characterized the fault permeability based on the calculated SGR using standard algorithms or tied to the well log core data to compare leaky faults versus sealed faults?
That's a great question, Neil. So let's see. The observed depletion. Yeah, the observed depletion is through faults with that don't offer membrane seal. That's true. We haven't really gone past the kind of the model stage, or like the stage where we derive the SGR. One reason why is because I didn't want to go too far into like capacity estimates, but also because we just kind of ran out of time to do some of those types of calculations. I know for a fact there are people doing this kind of transmissibility or permeability type calculations using SGR and also those types of standard algorithms that you're mentioning. Core and well data, I'm not so sure how much people are using that. There's not a whole lot of core in the Lower Jurassic. In the Upper Jurassic, yes, but not in the Lower Jurassic. But I'll just kind of punt again and say there are people working on this, Neil. So I'm really hoping that that people pick it up and kind of go forward with it. And maybe they prove me wrong. I don't really care, but as long as they kind of do what you're saying, I think it'd be really cool, because I agree it lends itself to a nice data set. So yeah.
Okay, great talk. Thank you. Your fault plane diagram showed major relay zones and overlaps between some of the major faults. My question, could fault segmentation play a dominant role in defining the size of potential sites?
Right. Let's see. Well, yes, that was a great observation. And, in the past, we focused a lot on this in earlier work, at least the relay zones and things like that. They do really allow for pressure communication and the flow of the drawdown pressure through those relays. But in defining the size of the potential sites, I think it does. I mean, they do reorient like the migration in some ways. I would say yes. And I haven't really done any analysis on, defining, the potential sites in that, like, you have the traps, and those can be used to kind of estimate how much you store, but they don't necessarily have to be the end place either. And, my job is more to do the research and not to really focus people on, like, in the paper, I wanted to focus on areas. Oh, this would be a cool place. This would be a cool place to store. Like, this is where you could put a well. But in the end, it's actually not. I wasn't really focused on that, because I thought leave it to the imagination of the readers to look at where to put wells and, brainstorm how you could combine those traps and so on. But yes, the segmentation it does play a big role in defining it, I think, because you can have the CO2 plume pinballing a little bit along some of these faults, depending on the type of fault mechanism, the seal mechanism they have, like juxtaposition seals. So yeah, it does.
Okay, next one is, how closely do you think drawdown related pressure behavior approximates the injection related pressure increase when at a commercial injection scale?
It has to play some role. I think you could use it to back calculate or to kind of calculate something like that. I'm sure, again, somebody knows how to do that. This is not really the modeling, that type of modeling, reservoir modeling, things like that. That's not really my expertise, but I'm sure people know how to do this. So I think you can use the drawdown pressure to approximate injection and so on. So injection rates and safe injection rates, especially when you link it with the geomechanical work. So I think it can be used.
Okay, great presentation. Many thanks. How about fault reactivation and cap rock integrity issues due to injection? How much is maximum pressure to avoid fault reactivation?
I don't really remember how much the maximum pressure. There was just a paper by Thompson and a few people from Equinor that just put out a paper on the stress field and some of the stuff. But and also a colleague of mine, John Mueller, I mean, he's put out a couple of papers now on the fault reactivation and the caprock integrity. Monsar's also put out. There's a few people at University of Oslo who've put out some papers on doing mostly through geophysical methods and petrophysical methods, not through you know, core or any other kind of methodology, but mostly through geophysics and petrophysics, done caprock integrity. And from injection, I'm not sure if they did any calculation on or used their results to see what the injection would do to it, but I think their results showed that the caprocks were good. So yeah. But what I do know is that the lower Jurassic caprock, so that Drake formation, is a little bit more brittle than the upper.
Okay, unfortunately, that's all the time we have. There are more questions, but I would encourage you to reach out to Johnathon to inquire with them. Johnathon, this has been an excellent talk, and I look forward to reading more about your research.
Cool. Yeah, absolutely. Thanks. Again, I'll go to my email again. I guess I don't know. I guess they're recorded. So, but yeah, I really appreciate you allowing me to share the work, and yeah, I'm looking forward to kind of the future of this industry. But thanks a lot, and can't wait to see the next talk next month. Okay.
Yeah, it's going to be great. All right, thank you, everyone, and we'll be posting the next talk in the coming days. Thanks.